Okay, yeah, so today I'm going to be talking about cosmic rays, in particular how cosmic rays allow us to access the highest energies in the universe. And particularly before particle accelerators were a thing, cosmic rays were how people tested the basics of particle physics. And this is something that's still ongoing today. And so I'm going to talk a little bit about what they are, and in particular the history of how we discovered cosmic rays, which is somewhat recent. Then I'm going to talk about basically how do we observe them and how do we see them and infer their properties. And finally, I'm going to spend a little bit of time talking about how do they move and influence the rest of the universe. So what are they? So in the early 1900s, when people were first starting to think about atomic physics and particle physics wasn't really actually a thing yet, and people were in the laboratories trying to measure all these properties, a lot of their instruments that were set to measure ionizations for radiation, which if you're in a lab that deals with things that have radiation, you want to make sure that your lab is shielded as best as possible. And so you wanted to try and make sure that the instruments that measured that radiation said that there was no contamination. And they found that no matter how well they shielded their labs, their instruments always measured an ionization from radiation. And this is quite troubling if you are trying to make a completely clean environment. And for a long time, people couldn't really figure out what was going on. And there was a lot of explanations saying that at the time they knew that the Earth's crust had radioactive materials like uranium in it that would be causing this. And that these ionizations were thought to be gamma rays. And so to test this, they wanted to figure out, okay, well, if it's coming from the Earth, then the best way to test it is to go above the Earth. And if it's coming from the Earth, it should decrease. And so Victor Hess, who's an Austrian-American physicist, in 1911 and 1912 did exactly that. And he took several balloon flights where he got into a balloon that's him in the center there, and went up with some instruments and measured the ionizations as he got progressively higher and higher. And he did a series of balloon flights. You can kind of see it going through here. There's about a handful of balloon flights where he did this, and he got to, I think, nearly a mile up in the air, if not a little bit more. And what they were expecting, if everything went according to plan, was that the ionizations would decrease as you go higher and higher. What they found instead was completely different. So the blue lines here are the ionizations as a function of the altitude above the ground. So if it was coming from the Earth's crust, you would expect it to go down. And they found it instead to go up. Hess has since then been credited with the discovery of cosmic rays, because when he discovered this and he saw this, he said, well, if it's getting if there's more ionizations, meaning more of this radiation as we go higher up, it must be coming from space. Now, he's been largely credited with the discovery of cosmic rays, and he received the 1936 Nobel Prize for doing so. But in fact, a year earlier, and this happens fairly often in physics, more so than we would like to admit, there was an Italian physicist who did a different thing where he took the same instruments, or similar style instruments, and instead put them underwater. So instead of going up, he went instead to the water and said, okay, if I can get closer to the crust, then it must increase. And unfortunately, the paper is entirely in Italian, which might be why other people didn't read it. So if you don't know Italian, if you do know Italian, you can read this and great. A recent translation was posted, and he wrote in 1910, in fact, that this radiation has an origin independent of the direct action, basically, of the stuff in the crust. So this was done in 1910. Hess's measurements were done in 1911 and 12. Hess's papers actually never cited Pacini's papers, and apparently they had some letters back and forth where Hess was super apologetic because he'd never heard about it before. Curiously, the reason why he doesn't get a lot of the credit is because the Nobel Prize for it was given out in 1936, and he died in 1934. So you can't get the Nobel Prize if you're dead. So Hess got the Nobel Prize instead. And since then, people have almost unilaterally said that Hess discovered cosmic rays. Unfortunately, things like that happen. And luckily, you know, there's historians who go back and find things like this. And so at the time, what they knew was that the source of this radiation was coming from space. They were guessing that it wasn't coming from the sun, but coming from something else. So they had some measurements that seemed to suggest that it wasn't directly correlated with what was going on with the sun. Almost every major theorist at the time said, it's gamma radiation. We know what gamma radiation is. That's great. And of course, to the theorist's nightmare, an experimenter said, well, let's go test it. So this was later tested. And what was done was people took instruments and basically moved around the Earth. And what they found was that as they moved in latitude, the amount of this ionization changed. So that means that the ionization is somehow being deflected off of the Earth's magnetic field. Well, photons don't do that. The only thing that is deflected from a magnetic field is a charged particle. And so this led to this notion that has since been accepted, that these ionizations are caused by cosmic rays, which are incredibly energetic charged particles that are basically coming from outer space and coming through the atmosphere. So what do we know about today about what they are? So this is the most recent and kind of best spectrum that we have of cosmic rays from basically the mass of the cosmic ray. So the mass of a cosmic ray is 1 giga electron volt, or 10 to the 9 electron volts. Anything above that, so if it has an energy above that, then it's a relativistic particle. So it's moving faster than its mass energy. And so far, this is kind of the best we have. It goes from 10 to the 9, so 1 giga electron volt, to 10 to the 20 electron volts, which is 1 exa electron volt. I didn't even know about this prefix until I started studying cosmic rays, because even for astronomy, 10 to the 20 is a big number. What they found was that, I mean, if you look at it, it's pretty unremarkable. Like, it's just a straight line. Now, there's some good things and bad things about that. The good things about that is that there's a lot of very simple theories that can describe this. The bad news about that is that we can't actually figure out how to get cosmic rays up to these energies. And so when we look at some of these kind of moderate energies, like a tera electron volt, which is about here, those can kind of maybe be explained by supernova explosions. Up to around 10 to the 18 or 10 to the 17, you can maybe explain those with the black holes in the center of galaxies, which we just heard about. But how to get these really high energy ones, really nobody knows. And for reference, is shown here that the Large Hadron Collider can only access energies below this limit. So the benefit of cosmic rays is that we're able to get nearly a billion orders of a fraction of a billion in energy of particles to test basic physics with. And so this is something which has been going on for now a long time. And so these very high energy cosmic rays are being used to test things like quark physics and everything else like that. And in terms of what cosmic rays are made up of, so I said they're charged particles, but there's a lot of different kinds of particles. Dominantly, they are hydrogen, but a charged hydrogen is just a proton. And then helium and lithium, basically all of the atoms that have up all the way up to look like strontium. Basically, these are fully ionized atoms of these. And so something like iron, it's what has accelerated that iron atom was able to strip off all of the electrons of iron, which is very difficult to do. So the blue here shows what the cosmic rays seem to be made out of, and this is in part due to some ground-based observations and also observations in space-based instruments on ISS and Voyager. This red is what we think basically the solar system abundances are like. So this is the abundances of these atoms in our sun. And there are some big differences. So there's a huge amount of things like lithium and boron cosmic rays, but we don't see that in our solar system. And there's a lot of these other kind of enhancements. And these enhancements tell us exactly about things with particle physics. So when a cosmic ray hits something else, it might shatter that thing and create all these others. So that's a little about what they are. So how do we actually see them? So we see cosmic rays basically in two different methods. The first one is the indirect methods, and this is creating some kind of showers in the air. So what happens is, let's say you have one of these super high energy cosmic rays, and it hits the atmosphere of the Earth. And the Earth's atmosphere is incredibly dense compared to the gas it was traveling in, and the Earth also has a nice magnetic field which deflects it and also affects it. And when it hits the atmosphere, that, let's say it's a proton, will basically immediately shatter and create pions. And pions are some elementary particles. Those pions then can decay into muons and gamma rays and electrons and positrons and all of these things. And so we can detect those showers. The other thing that happens is when a particle enters gas or something that isn't a vacuum, it can actually be traveling faster than the speed of light in that material. And so what you get is Cherenkov radiation. This is seen in nuclear reactors. It's this blue light that they show these pictures in the reactors on. In this case, the speed of light in the material is the speed of light in the vacuum divided by its index of refraction. So something like water has a higher index of refraction. So you can have particles that go faster than light would in that material, and that creates kind of an analog would be like the bow shocks from like a plane going supersonic. You get similar with light, and that tells you a lot about how fast that particle is going, what energy it is. And let's see if we can play the movie. So this is a simulation of a shower that would happen, for instance, over Chicago, where there are some detectors, and so this is the kind of Chicago area, and you see a cosmic ray way up in the atmosphere, starts falling, and as it's going through, it's creating a little bit of a shower. Then you see all of these things going on. So this is a shower of particles, which is basically falling over a fairly large area of Chicago. Happens all the time, and so their detectors might be placed, for instance, down here, and they would measure that shower. They can measure the angle of the shower, they can measure all the particles, and from that they can determine much of the properties of what that original cosmic ray was. But to do that, they have to know about the particle physics that would create all these particles. And so in measuring these showers, they're able to directly test particle physics and astronomy, which is kind of cool that you get both at once. So this is one example of an indirect method observatory. So this is, there might have been talk at some point about IceCube, which is done in the Antarctic. This is Ice Top, which sits above it. And every site here you see has two little detectors, so that when a cosmic ray, an energetic particle, hits and goes to the ice, it will emit this radiation, and it will create a signal which they can then track. And so if they know the angle of that signal, they can detect all the light, they can know what the energy of that particle was, and they can use some other instruments on there to detect things like the mass of the particle. So one of the things that you have to do for this, though, is you have to create some very large arrays spatially. So this one, I believe, is a square kilometer. There's some other ones that have been built that are like 10 square kilometers. The larger area you get, the more sensitive you get, the higher energies that you can probe. So another way that you can indirectly test this is, instead of waiting for the showers to hit the ground or waiting for the cosmic rays to hit the ground, is you can point a telescope up into the atmosphere and wait to see that light. And so this is HESS, and HESS has been recently doing surveys of the galaxy in particular, looking for this radiation as particles basically are going through the Earth's atmosphere at relativistic energies. So finally, so this is a result from HESS. I'm sorry if you can't see this. So this is the Milky Way as seen in carbon monoxide. So you see the disk of the Milky Way here. And if you look at this in HESS, this is looking at radiation from gamma rays that are greater than 1 TeV. And you see it basically looks exactly like the plane of the Milky Way, where many of these things are like supernova remnants and other sort of bubbles. So in order to generate these cosmic rays, what you really need to have is some sort of energetic event, something which is either explosive or something which is able to inject a lot of energy into particles really, really fast. So another way to do indirect methods is by going into space and directly observing the gamma radiation that is propagating through the universe, not from gamma rays that are hitting the Earth's atmosphere or anything, but these are gamma rays that were produced when cosmic rays hit other things out in space. So this is a map of the Milky Way with the Fermi telescope, with gamma rays greater than 1 giga electron volt. And you can see basically it covers exactly the same. You can kind of look back to this one. This is it in carbon monoxide, and this is it in gamma rays. So the gamma rays are tracing where the cosmic rays are hitting this cold and dense gas, and basically, shattering and creating gamma rays. And those gamma rays are then traveling through the rest of the galaxy to come to the Fermi telescope. Unfortunately, there's not a lot of gamma ray observatories. So if Fermi goes out, we are stuck with nothing for a while. So people are hoping that gamma ray that Fermi is good for a long time. And in particular, none of the big observatories that are planned for the next decade are gamma ray observatories. So the other way that we can detect cosmic rays is directly. And one of the more kind of famous instruments that did this was Voyager 1 and 2, where they had their cosmic ray units were all here. And what Voyager does is it directly detects the particles hitting their instruments. And in fact, a little while ago, there was this press release that came out and said, Voyager has left the solar system. And I think there was an Astronomy in the News about that as well here. Unfortunately, it looks like it maybe has not actually fully left the solar system. And the way we can detect that is by looking at the spectrum that it measures in cosmic rays. So the sun's magnetic field deflects a lot of the cosmic rays coming from the galaxy. And so what was the hope was that as Voyager kept going out, you would see all of a sudden the total amount of cosmic rays all of a sudden shoot up. And it did that, and that's why they said, we've left the solar system. That's great. But it looks like it maybe hasn't fully left the solar system. So this is the spectrum of cosmic rays observed on Voyager for hydrogen atoms and helium atoms. And the energy scales that Voyager covers are much, much lower energies. And so the previous panel kind of started basically at the end of this plot. And so this goes to 10 MeV, or mega electron volts, so 10 million electron volts, and you see it's no longer a nice straight line. It starts to curve off, and this curving off is currently unknown. The physics is currently unknown. Whether or not this is a feature of the spectrum that we would see in space, or whether or not this is still because that the sun's magnetic field is deflecting a lot of these lower energy cosmic rays. And most of my own personal work is looking at the injection of these lower energy cosmic rays into the Milky Way. So how do they move? So as I mentioned, cosmic rays are charged particles. Charged particles, unfortunately, couple to magnetic fields. But if you know anything about Maxwell's laws, you know that a moving charged particle also creates a magnetic field. And so now you have a case where something is spiraling along a magnetic field at super high energies, and while it's doing so, it's also creating magnetic fields around it. And this has led to an incredibly problematic issue in theory, in that you need the magnetic field to solve how the cosmic rays travel, but you need to know how the cosmic rays travel to solve for the magnetic field. And for about 6 decades, no one has really figured out how to solve this problem. Besides doing very, very, very simple problems, taking up millions of CPU hours to do an incredibly simple problem. So typically, people use 1 or 2 approximations where they ignore the magnetic fields of the cosmic rays, or they kind of just ignore the cosmic rays. And so this is kind of how they travel. Unfortunately, PowerPoint doesn't have a spiral, so I had to hand draw it, and you can tell why I went into science and not art. Luckily, the circle was a tool, so I didn't have to draw the circle. And so the black line is the magnetic field, and the particle, like a proton or electron, would just be spiraling along this magnetic field. So if the magnetic field warps, the cosmic ray would go with it. And so the radius at which it kind of rotates around it is related to the energy or the momentum of the cosmic ray, and inversely related to the strength of the magnetic field. So basically, if you have a very strong field, the cosmic rays are going to be very tightly spinning around it. And if you have a cosmic ray that's going very fast, it might actually be able to have enough energy to kind of spiral its way off the field. But of course, this is one of the approximations where you ignore the fact that the cosmic ray is actually there creating magnetic fields, because that would not make this picture look... My drawing skills are not that good. So the other thing that happens as they're traveling through the gas in the galaxy is very similar to what happens when they travel through the atmosphere, is that the proton will collide with some gas in space, and it will shatter. And it will create all these other particles like pions and muons, and gamma rays and electrons and positrons and all the other the particle zoo. And so they not only have to spiral along magnetic fields, but then they start to lose energy over time. But when they lose that energy, they're giving that energy into the rest of the gas around it. And so because of this, cosmic rays can actually couple to the rest of the galaxy quite well. And in fact, when you take the Milky Way and you kind of portion out all of the energy in the gas, about a third of the energy comes from the magnetic field, about a third of the energy comes from the thermal energy of the gas, and the other third comes from the cosmic rays that are going through the gas. So the cosmic rays are incredibly important, and the magnetic fields are incredibly important. Unfortunately, magnetic fields and cosmic rays are two of the hardest things that a theorist can ever deal with. And so it's only been in the past few years that theorists have been able to actually include cosmic rays and magnetic fields in simulations of how galaxies evolve. So for the previous many decades, when people simulated the gas of a galaxy, they were ignoring 2/3 of the energy that would be in that gas, because no computing cluster would ever give you the amount of time. Like, you can't just write a thing saying, I want 1 billion hours and I don't know how to do this thing, but trust me that it'll happen. We've tried, it doesn't work. But this is one of a recent simulation that has been done of a kind of a piece of the Milky Way, and there's 3 panels here. So the first panel is a portion of the Milky Way. So this is looking at like the disk of the Milky Way, and this would be looking at it from like the top down. If you only included the thermal energy, and then this one is if you only include the cosmic rays and the magnetic field, and this last one is if you include everything. And I actually know the people who ran this simulation, and this one took about 5 or 10 times longer to run. So I think total these took several million hours on a cluster to sit there and run. I can find the mouse here. There we go. And so just the thermal energy, you kind of just have a disk that sits there. It kind of collapses in. And so one of the biggest problems that people have had with galaxies for a long time is we see these winds coming off of galaxies, but if you just did a simulation like this, you could never actually get winds coming off of galaxies. But the moment you include cosmic rays basically fling all of this gas from the Milky Way, and instead of creating a very patchy disk, you create something that's much more smooth with just a few high dense areas. And this is kind of more similar to what we actually observe. And so the next generation of simulations of the galaxy and maybe even of the universe will finally start to include cosmic rays. It took about 100 years to do so, but we finally have the computers that can start to do this. We finally start to have the computer algorithms to also solve all of these equations. And so the next probably 5 or 10 years of theory is really starting to obsess over what happens with the cosmic rays. What happens now if we include that last 66% of the energy in the gas into these models. So any questions?
Good job. As promised, we are going to read Twitter questions first. Unfortunately, the person who promised this is the one who asked the Twitter question. So this is from our host, Aaron, and he might have a little bit of background knowledge on the subject, so sorry. Second speaker, your dissertation includes studying how cosmic rays influence how stars form. Can you give a 2-sentence summary of your dissertation work for us?
Yes. Yeah, so my dissertation work has focused on those lower energy cosmic rays. And there's been this long-standing problem in astrochemistry where the cosmic rays basically do everything with the chemistry. But no chemistry code up until 2 weeks ago included cosmic rays into their calculations. And so most of my dissertation work has been trying to understand how the cosmic rays propagate through the gas in which stars form, and mostly in particular how it affects the chemistry of that gas and how it affects the chemistry of star formation.
Nice. So I think we can just give you your doctorate now, right? That's it? You're done?
It would smooth the paperwork over.
Yes.
I've always thought of cosmic rays, or at least charged particles, that they're just protons. You seem to think that we have much more complex molecules, not molecules, but atom core nucleus is coming, like iron. Iron is remarkably hard to make, okay? And we're seeing that come to us from the void. It seems odd.
Yeah, so
Can you repeat the
protons
question?
are, yeah, so the question was that basically it was, you know, he thinks he had previously thought that most of the cosmic rays are protons, but I showed that it goes all the way up to like strontium, for instance, and kind of how does that happen, I guess, is what your question is, or really how sure do we know about it. So the protons are probably the easiest ones to figure out, because the physics is a lot simpler for what happens if a proton just hits the atmosphere. However, what you can do is you can independently measure the energy and the velocity. And if you can independently measure both of those things, then you can get the mass. And if you have the mass, then you have the atom. So when they do that, they assume that these atoms are fully ionized. And so, for instance, in the radiation case, the amount of radiation is dependent in part on the energy of the particle, but the size of the cone is dependent on the velocity. So if they can measure both those things independently, then they can figure that out. I'd say for probably up until some of the most recent ground-based measurements, and say since the 90s or so, it was largely thought that it was just protons. Now, the difficulty is in figuring out how to get them to that energy. No one really, there's been no good theories yet to say how do you get an iron atom to 10 to the 18 EVs. So far, no theory can actually do that. The upside of that is that means that it will take people a long time to do that, so that's good job security.
All right. Anybody up top? Right here?
So, in the plot of capture of the particles that are, the ions that are coming from the Milky Way, if that was, you know, if this was instead like you had another dimension that was measuring the ridiculously high potential particle, like 100 greater, does it look the same? Is it centralized with these higher potentials?
So the question was, if you look at this, but instead of you know, kind of the total energy, if you looked at it in different energies, say going up in energy, right? Does it like centralize, or what does it do? So unfortunately, some of these instruments can't do that, where they're basically just sensitive to anything above a threshold. However, there have been some who have looked at. So this is everything, for instance, above 1 GeV. If you look at what happens with above 1 TeV, then you have HESS. And HESS has this plot here down here where it's even more thin. So the higher energy you go, the more you're kind of selecting out where we think that it's being accelerated at. So for this case, at the very high energies, you literally just see these little tiny bubbles. But that could also just be the fact that this is much lower resolution than Fermi is.
All right. Yes, by the bar.
So by including all this new gamma ray data, what kind of answers do you expect? I guess, like, what are you guys trying to search for? What are you hopeful to find?
Okay, so the question was, given all of the kind of gamma ray data and everything, what are we hoping to find? So there's basically two big questions right now that are people who do cosmic ray stuff. I'm not I don't focus entirely on cosmic rays. And people who do that actually call themselves astroparticle physicists, which is a kind of a cool name. So there's a couple really big questions. So there's a few features here which they call the knee and the ankle as you go to higher energies. It's entirely unclear how that happens.
That happens because astronomers shouldn't name stuff.
Exactly. So, I mean, if you look at it by eye, like, you can't actually tell that there's something there, but they do a fit to it, see a difference, and call it a knee. What they think is that this is a change from something that goes from, like, things in the galaxy to things that are extragalactic, and then big question mark. There's also this, like, just cutoff at around 10 to the 20, even though their instruments should actually observe things higher energies, but they don't see it. So that's another big question. I'd say the most problematic thing that we still don't have a good answer to is how do you accelerate cosmic rays, where for decades people said supernova are the only things that can do it. It must be supernova. And the reason why they said this is because they looked at, for instance, X-ray images and gamma ray images, and you could see the supernova bubbles, and it's very clearly shown. But when people have kind of done a bit more thorough and recent calculations, supernova might not actually be able to explain it. So if supernova don't explain it, that takes out our one good explanation for this whole range. And there's no other explanations for how to generate something this high energy in the Milky Way besides a supernova. So if it's not that, we have, unknown physics. We have no idea what's going on.
So on that note, let's thank our second speaker,